Hey guys, today we're going to be talking about calculus for machine learning, which is a little bit different from the past lectures, as previously we lectured on topics directly related to machine learning. And the reason we're doing a calculus lecture right now is because the next few lectures are going to be on neural networks. And while those lectures will not necessarily be math focused, a lot of the math behind neural networks is going to be covered in today's lecture so that it'll make sense when you see it in the future. And of course, this is a pretty short lecture for all of the content that's going to be covered. So there's additional material linked in the last section of the lecture, and you can just type in the chat if you have any questions. So, getting right into it. What is a derivative? The definition of derivative is the rate of change of a function at a given point. So let's look at a simple example of this, a line. So in the lecture, you can see there's a line given that's y equals 3x plus 8. And the rate of change, given the equation f of x1 minus f of x naught over x1 minus x naught, can be found as 3. But in a line, the rate of change between any 2 points or at any point is constant because that's defined by the slope. So let's take a look at a more complex curve to see how we can apply derivatives to nonlinear functions. We're going to use the parabola y equals x squared, and that's the red curve. And the blue line is just the line y equals 2x. So let's find the derivative at x equals 1. So given what we know about lines, we could approximate the derivative as the secant line between 1 and a number a little bit bigger than 1, because that ought to be close to where the curve actually lies. So we can see that when delta x is 1, so when we're looking at the secant line between x equals 1 and x equals 2, the slope is 3. And as we decrease delta x and get it to 0.1, it becomes 2.1. When we get it to 0.001, that gives us a slope of 2.001. So this this slope does appear to be approaching 2 as delta x continues to decrease. Also, we could make a note here that the purple line is when delta x is 1, and the blue line is actually right at the tangent of the parabola at x equals 1. So we can kind of see that from the purple line to the green line, it's starting to bend closer to that line. So the limit definition of a derivative is that as that delta x decreases, our secant line becomes closer to that tangent line at the curve, and therefore the slope of that tangent line is the rate of change at that point. So you can see in the limit definition here, as limit of delta x approaches 0, f of x naught plus delta x minus f of x naught all over delta x gives you the limit definition of a derivative. And there's a couple ways that derivatives are expressed in equations. So a couple shown here are seen as f prime of x, dy over dx, df over dx, d over dx times f of x. Okay, so thankfully we have derivative rules, so we can take the derivative of a function without having to use the limit definition every time. Using the limit definition every time would be not only difficult or nearly impossible sometimes, but also very time-consuming because we would only get the derivative, the number, at a single point at a time. So there are a few basic rules we're going to run through. And these rules, we're not covering all of the rules of derivatives because that would be quite long, not all related to what's further down in this lecture. Like, for example, we're not covering any trig rules, but we're going to cover a few. So the power rule is given a function f of x in the form x to the power of n, the derivative of it will be n times x to the power of n minus 1. So an example of that would be f of x being x to the third. So that means that the derivative of that would have to be 3x squared. Cool? Okay. So there's a special function e to the x, where the derivative of e to the x also equals e to the x. So the slope at any point in the function is also equal to the function. And one more is f of x, given that f of x is ln x, the derivative of that is 1 over x. Of course, not all functions we're given are going to be that simple or that clean. So thankfully, we have rules to address more complex functions. The first one is the chain rule, and this one is the most complex of all of the other rules. So the chain rule is used for functions that look like they have functions within a function. So for example, the function f of x equals e to the 3x squared. It's in the lecture in section 2.3. The outermost function is the entire function, and the inner function that we see is 3x squared, right? And we can't just take a single derivative of e to the 3x squared, treating 3x squared as x, because we don't account for the change that the inner function is creating to the outer function. So in the chain rule, it just shows that we'll take the derivative of the total outer function and multiply that by the derivative of the inner function. So instead of doing all this talking, I'll just walk you through taking the derivative of this function. So the derivative of the outer function, e to the 3x squared, is equal to e to the 3x squared if we just applied our e to the x rule, right? So then we have to multiply it by the inner function, which has a derivative of 6x. So our final derivative would equal 6x times e to the 3x squared. And of course, the chain rule can apply to a function within a function within a function, however many times. You would just have to account for it. So in equation 3 on the lecture, it shows three functions, 2 of them nested in the larger one, and that you just repeat it. So if you're looking at f of g of h of x, it'd be f prime of g of h of x times g prime of h of x times h prime of x. Okay, now that that's out of the way, the other rules are much easier to understand. So the sum rule is very basic. Given that a function is the sum of 2 other functions, the derivative of that function will equal the sum of the derivative of the 2 subfunctions. The product rule can be applied when we have a function that is the product of 2 smaller functions. So in this, so that would mean that the derivative is the derivative of the first function times the second function plus the first function times the derivative of the second function. So if we wanted to try that out on a product, just say 3x times e to the x, g prime of x would be 3. So we'd have 3 times e to the x plus 3x, and then the derivative of e to the x is e to the x. Okay, and the quotient rule is quite long. So there's a kind of not quite rhyme, but sing-songy pattern they teach in calculus to make it more digestible. Down, d up, minus up, d down over down, down. So when we look at this, down is the denominator, so h of x times d up, which is like the derivative of the numerator, g of x, minus up, g of x, d down, derivative of h of x, over the denominator squared. Okay, so down, down. Cool, cool. So let's try actually applying all of our rules to take a derivative of the sigmoid function. So we're going to be seeing the sigmoid function, which is s of x here in the second bullet, in next week's lectures or the weeks after, as it's often used as the activation function in neural network applications. Okay, so might want to first take a moment to see how you could take the derivative of this function on your own, or you could pause the video for a moment to think about it. But going right ahead, because it's a fraction, we could first see it and then decide we want to use the quotient rule on it. So the up function, or the numerator function, would be 1, and the down function, denominator function, is 1 plus e to the negative x. The derivative of the up function is 0, and the derivative of the down function is negative e to the negative x using the sum rule and the chain rule. So looking at the sum rule, we first take the derivative of 1 and it's 0, so we're just accounting for the derivative of e to the negative x. And using the chain rule, we can use the outer function, which is e to the x, apply it, so it's e to the negative x times, and then the inner function negative x, and the derivative of that is negative 1 through the power rule. That was a mouthful. So then when we plug these values into our quotient rule, it's a little messy, but we end up with e to the negative x over 1 plus e to the negative x, all of that squared. Okay, so now that we have the sigmoid derivative, let's see if we can write it in terms of s of x. So automatically looking at the derivative of the sigmoid function, we can factor out s of x out of s prime of x, because the denominator of s prime of x is just that of the denominator of s of x squared. So that gives us s prime of x equals s of x times e to the negative x over 1 plus e to the negative x. Okay, so basically to the numerator of the fraction we still have, we can do plus 1 and minus 1. And then we can split that into two more fractions. So it becomes 1 plus e to the negative x over 1 plus e to the negative x minus 1 over 1 plus e to the negative x. And then here, can we see another s? It's in the minus 1 over 1 plus e to the negative x. So we can see this derivative of the sigmoid function equals the sigmoid function times 1 minus the sigmoid function, which is cool because when we're programming, we don't actually need to, we can just use the sigmoid function in order to find the sigmoid derivative. Okay, so all of that information we just talked about was in 2 dimensions. And unfortunately, neural networks have many variables, which means that we can't just take a derivative and call it a day. So gradient descent is what this is going to be mostly used on, and that's basically working backwards using the error or the cost of your function to adjust your neural network. And a neural network, I wrote essential, I meant essentially, is essentially a chain of functions. And because a small change in one function will affect the next function, there's dozens of variables affecting the neural network. This is sort of analogous to in the chain rule, how we have to account for the small mini functions affecting the larger function instead of just taking the derivative of the whole thing. If that didn't make sense, just ignore it. So we can't use a derivative to find the change in the function in n dimensions, so we have to use gradients, which are analogous to derivatives, but they can be applied in multivariable contexts. Okay. So we know that a derivative is telling us the rate of change of a curve at a certain point. So, and that's pretty easy for us to visualize because we often think in 2D. So we're going to look at a 3D application because 4D would get quite complex. But you can see it in this graph as the gradient of any point would be the opposite of where you would put a small ball on here. So just say I'd put a ball here, and the ball would naturally fall down into this groove, right? The gradient would give us the opposite direction. So the gradient would give us a little vector pointing up here. So now that we've said that, let's talk about how we can actually find this vector. So a gradient, that's a nabla sign before the F. are vectors that express the rate of change of the function per each variable because there's several variables affecting it. So a partial derivative of the function with respect to a variable, let's just call our example variable x, is written as partial of f over partial of x. So the gradient is a vector of these partials. So for a 3D function, it would be partial of z over partial of x, comma, partial of z over partial of y. And then in more dimensions, it's the same. So in a 4D function, it'd be like partial of z over, or partial of w over partial of x, partial w over partial of y, and partial w over partial of z. And I know that lecture was a lot, so make sure to check out the links if you want more information. And the images not already cited are from GeoGebra, Desmos, which I both really recommend. GeoGebra specifically if you're trying to model 3D surfaces, and Kevin Fu's last year lecture of the same title. Okay, thanks for sticking with me, guys.